We're going to now establish derivatives for the constants and for polynomial functions. So first let's do the constants. It's a pretty simple calculation. Everything's going to be based on the limit definition of a derivative, which we've already covered. So the first thing is, let's suppose you have some function which is equal to a constant. Notice that this is f of x and it depends only on a constant. So as an example function, f of x equals 5. The function f of x equals 5 is of course a horizontal line passing through a y-intercept of 5. The derivative of that, remember derivatives are interpreted graphically as slopes of tangent lines. So the slope of the tangent line at 5, if this is 5, slope of this tangent line should always be 0. It's a linear function. We already discussed that linear functions' slopes are their derivatives, but let's just establish that for the constant case. So if we consider f prime, that's again the limit as h approaches 0 of the function evaluated at x plus h minus the function evaluated at x all over h. So this is going to seem a little bit strange and maybe even trivial to you, but is a necessary part of the process in establishing that what the constant's derivative is. So first thing is, think about what f of x plus h is. That is, when you plug x plus h into this function, what is it? Sorry for the bell. So if you plug x plus h into this function, this one, or more generally this one, you just get c. And if you move over a little bit to f of x, it's still c, right? There's no x value to substitute in for. And then you divide by h. And we can see pretty clearly that this limit, 0 over h, it really does not depend on h, right? It's 0. And if you think to yourself, but wait a second, when h is 0, sorry, just closing the door. If you think to yourself, when h is 0, that's going to be 0 over 0, which is undefined. But remember, the limits are paying attention primarily to what happens in the behavior around the area as opposed to what happens at the specific value when h is 0. Think about this fraction, it's always 0. No matter how small h gets, this fraction is always 0. Okay, so we've established that, for example, if I gave you, in this case, if the function was equal to 5, then its derivative, which I'll put in red, is 0. And again, that should follow from the result that we'd already established about the derivative of any linear function. So the derivative of this linear function is, of course, its slope, and since it's a constant function, it's 0. Okay, so now we're going to move on to further study of polynomial functions. Of course, we could have x to some power. We've only really dealt with x to the first power so far. We did a quadratic one as well, but now let's look a little bit more generally at something, or much more generally, at x to the n. So let me just redefine a function. So the function will be, as I said before, x to the n, and this n value we can have as a rational number. So as long as this thing is rational, we're fine. So maybe I'll make a statement here that n is an element of Q. Just to remind you about this notation, is an element means n is a member of Q, and if you're wondering, Q, rational, well, think quotient, right? So we're going to take the derivative of that. And remember, if we don't know the derivative, if we don't already have a shortcut for it, we need to appeal to the limit definition. So f prime remember, it's f of x plus h. I'm not going to write that part out now. I'll just substitute x plus h directly in. I don't want this to be confusing to you. That is an h. That is an n. And then we're going to subtract from that f of x itself. F of x is simply x to the n, and we're going to divide by h. Now we're going to need a little bit more space for this next line. This might be a really good opportunity for you to pause and think about this. But what I want you to think about, maybe you'll click pause in a second when I finish this thought, is the fact that this thing needs expanded. And I use the word this thing because I want you to think about what exactly is x plus h if you were to name it. You know, put yourself back in Algebra 1 and you're naming it, what is it? And that will lead you to something that you can use that you've previously established in previous years. Okay, so maybe pause here. Okay, if you came to a conclusion that, hey, that thing's a binomial, that is a very good thing. It definitely is a binomial, and of course we can use the binomial theorem to expand it. So again, this might be a great place to hit pause and go look up the binomial theorem in a formula packet or in your book or something like that. So the first term in the binomial expansion of this is clearly is x to the n. But remember the binomial theorem, for each term we'll have n, this is a choose argument, n choose k, and that'll be x to the k if we're doing x plus y. Right. So each term will n choose k, x to the k, y to the n minus k. Now, this just gives you, I shouldn't say that this whole thing is equal to this. This whole thing is equal to the sum of these expressions. So I guess I could maybe edit my formula a little bit here to involve the sum of all of them. Major point is here, this will serve as our model for each term. So our first term will have x to the n. So that's all of our expansion will be involved, just x in the first term. So the y value, or the second thing, should be to the 0. So we'll have x to the n. And notice it would, if you replace k, actually I'm going to change k's color. If you replace k with whatever value you're on, I should change it here. So for example, if we're dealing with the x to the n part of this, then there must be 0 h's involved. So it'll be n choose n, which will result in 0. So that'll be x to the n, y to the n minus n, and then you'll get, of course, y to the 0, which is 1. So that's our first term. Our second term is going to be n choose n minus 1. By the way, side discussion here is that n, or let me do this numerically. Binomial theorem can be listed in a couple of different ways because, for example, 5 choose 2 is the same as 5 choose 3. So 5 choose 2 is defined as 5 factorial over 2 factorial, 3 factorial, and 5 choose 3 is 5 factorial over 3 factorial, 2 factorial. So these two are the same, of course. So we could either think of the first term as an n choose n or as n choose 0 and then go from there. I've already stated it as an n choose n. So what I'm going to do for my next term is make it n choose n minus 1, which again would be the same thing as n choose 1. So n choose n minus 1. That's the coefficient of our term. X is raised to the n minus 1. And y will be raised to the n minus n minus 1, and that will be 1. I'm going to think about that one a second as well. And then we'll have lots more of these guys. And our last couple terms, if you think about the fact that the very last term in this expansion has to be all h's, right? That's h to the n. So the penultimate term, the second to last term, should involve n choose 1, because there's one more left, x to the 1, h to the n minus 1. So again, the brief summary of the binomial theorem is it starts by considering the first term of your binomial to be fully expanded, and it ends having the second term of your binomial to be fully expanded. So it starts with all x's, no h's, and then lose an x, gain an h. Lose another x, gain an h. Lose another x, gain an h. Until at the very end, you're left with no x's and all h's. Okay, now I have left off this term. So I'm just, again, color coding this to bring this guy down, minus x to the n. This is not part of our binomial expansion.